We come to the last section in this chapter, which is about angular momentum. So we're going to do this in analogy with the linear momentum from translational motion. Linear momentum, if you remember, was written as P, which is a vector quantity, which is mass times velocity. We did this in the chapter on collisions, yeah? And we have another relationship that we know about P, which is force equals change in momentum with time, yeah? So delta P over delta T. Delta P is impulse, yeah? So by analogy, we're going to write P as L in angular momentum. It's just convention, angular momentum is written with the symbol L. The analogous quantity to mass is moment of inertia, and analogous to linear velocity is our angular velocity. Therefore, L equals I omega. This is our definition for angular momentum. And this one, also by analogy, this is going to be my net torque is equal to change in angular momentum with time. Yeah? Important relationships. Let's look at a simple example to deal with some numbers here. Suppose you start an antique car by exerting a force of 300 newtons on its crank for 0.25 seconds. What angular momentum is given to the engine if the handle of the crank is 0.3 meters from the pivot and the force is exerted to create maximum torque the entire time? What does it mean? Force creates a maximum torque. That means R and F are perpendicular to each other. Yeah? So our torque is going to be R times F, yeah? Where R is the distance from the axis of rotation of the line of action of the force. So this is my force. This is my distance, R. Yeah. So torque equals R times F. Yeah. And we're interested in finding the angular momentum. Therefore, we need a relationship between torque and angular momentum. What was our relationship? Let's write it over here. So our relationship was angular momentum L, rate of change of this with time is going to give me the torque, the net torque, yeah? And I've just rearranged this equation to solve for delta L. So delta L equals tau times delta T. We know delta T, it's 0.25 seconds. Yeah, we know R, we know F. You just need to substitute the values in and multiply them. Okay. At the start, the initial angular momentum is 0 since we're starting from a zero rotation, yeah, to this final angular momentum, yeah. Okay. What are the units? Units are meters, newtons, seconds. So if you break down newtons into its constituent mass times acceleration, you're going to get kg meters per second squared. One of the seconds cancels out, gives you meters squared per second. This is the unit for angular momentum. Kg meter squared per second. Okay. And just like we had conservation of linear momentum when we had collisions in an isolated system, yeah, where there's no net external force, similarly, if we have no net external torque, then we will conserve angular momentum during rotation. Okay. So if an object is rotating, and its angular momentum at some initial time is, let's say, Li, and its angular momentum at some other time, let's call it our final time, is Lf, then provided there's no net external torque, we should have Li equals Lf. Yeah, that's the meaning of conservation of angular momentum. The key thing is we must have no net external torque. So mathematically, sum of torque equals 0. Then my initial momentum equals final momentum. And what is the definition for angular momentum? L equals I omega. So I can write this as I times omega, both at the initial time, equals I times omega at a final time. Yeah? And this applies to all kinds of objects. Macroscopic, which means objects at a large scale, and also microscopic objects such as atoms. Okay? So this has interesting implications. And let's look at one. You might have seen this on television in skating competitions, that if a skater is going into a spin, they try to bring their body in. So he has brought his arms in, he has brought his legs in as much as possible to his axis of rotation. Where is the axis of rotation? It's going top down like this, centered about some point. And he's going to spin around that point, right? So at the start, let's say he's in the spin, he has a certain moment of inertia. What has he done to his moment of inertia? He's made it as small as possible by bringing the mass in towards the axis of rotation, as much as possible. Remember that he's reducing that R. So I is small, L is fixed, then omega can be greater, So he's going into a fast spin. And when he comes out of the spin, the very opposite happens. He's increasing his moment of inertia by throwing some of the mass away from the axis of rotation, as much as possible. His arms are opened out, his legs are as far apart as possible. This is still the axis of rotation, but he's slowing down. Why does he slow down? Because it's that same L that's required. And now your I has become greater in that second diagram, and omega has become smaller correspondingly. So this is how conservation of angular momentum explains how things slow down when they rotate, or how they may speed up if you can change the moment of inertia of the object. Okay, we're going to stop here. That's the end of this chapter. Thank you.